The topic of this video is something about atoms that really is quite counterintuitive. So in our everyday experience, we can put any amount of energy into an object. So for example, baseball pitcher, he can throw the baseball, with any range of speeds, and it's a continuous range. That's to say that there's not only certain number of speeds that he can throw at. Whereas at the quantum level, down at the atomic level, the analogy would be a pitcher who could only throw the ball exactly 82 miles an hour and maybe 91 miles an hour, and that would be it, or maybe 3 different speeds. And so this idea that you can only have certain energies is called quantization. All right, so we're going to talk about the hydrogen atom. All right, and so at the center of the hydrogen atom is a nucleus, and the electrons just whizzing around. And this pattern is really quite random. It does not obey a circular orbit like you may have seen. And so the energy of the attraction of the electron to the proton is a certain number. And it's a negative number, and so I'll tell you a little bit more than the textbook does. And in the hydrogen atom, it's some sort of constant called the Rydberg constant for hydrogen, divided by an integer squared. And so one thing is that if you have opposite charges and you bring them in classically to where there's a distance of 0, the energy of the attraction is negative, and it's an infinite number. Well, that's not possible in hydrogen. First of all, the electron is around the proton, and so it has this energy level. And so the lowest n you can have is the counting numbers, 1. All right, so there's always a ground state, an energy level where you cannot get any lower than that. That's called the ground state. Now, there are other possible states for the hydrogen atom, but these are higher in energy. But they are quantized, and so the next one that you can have is the one where the integer is 2. You cannot have an energy between these two. Okay, the next highest energy. So this is the first excited state. All right, so in order to go from this level of energy to that level of energy, so the book uses the analogy of a bookshelf, and it's really quite good. In order to change the energy level of the atom, you have to add exactly that much energy. And one way to excite atoms is to absorb light. And so, for example, if you take a light of a certain frequency, and so the frequency is the number of waves per second. And this energy difference is equal to a constant, again, a different constant. It's called Planck's constant, times the frequency nu. All right, and so the thing you have to understand is that if the gap is larger, then it requires more energy and a different frequency, and as a matter of fact, a higher frequency. So when you look at the electromagnetic spectrum, that is what are the frequencies of light that we can see, and then beyond where we cannot see. So ultraviolet, UV from the sun, we cannot see it, but it's very high energy. And it's high energy because the light is a very high frequency. And high frequency has a lot of energy, and it's enough energy to break chemical bonds in your DNA and cause cancer. The smaller the energy gap, then the lower the frequency. And so that might be in the visible light. So you don't have to worry about being exposed to visible light. That's not going to have enough energy to excite electrons and bonds and give you cancer or anything like that. So anything below the ultraviolet is really quite safe. So try to understand these relationships between the energy gap and the frequency of the light coming out, and which end of the spectrum is high energy, high frequency. That's toward the violet end and past the ultraviolet. The low frequency stuff, small energy gap and low frequency. And that's like down red, below red, and in the visible range as well. It's pretty much safe. All right, so I want to preview what's going on with the distribution of the electron around the nucleus. When you look at this energy level, the probability of finding the electron is spherical and it's kind of fuzzy. You're more likely to find the electron near the nucleus and then outside. So if you see a spherical sort of thing, the shape of this is called an s orbital. All right, and that's the only type of shape you have for n equals 1. When you get to n equals 2, there's actually many possible probability distributions, all of which have the same energy in the hydrogen atom. There is one that looks like this. It's kind of spherical. It's larger. So the larger n corresponds to a larger s orbital. So that the two s orbital might look like great big sphere. The other type, and there's 3 of them, are called p orbitals. So and the 2 p orbitals, when you look at the illustrations of the text, kind of look like a figure 8. And one of them is going to be like in the x direction. One will be in the y direction, one will be in the z directions. Of course, there's 3 directions, x, y, and z. That's why you have 3 p orbitals, called px, py, and pz, depending on which direction they're pointing. As you go up another level, you get new types that are possible. There's an s-type. There's a p-type, and then finally, there's a new type called d. So it turns out every time you go up in the energy level that you have all of the previous types at that new energy level and a new type. So if you go to n equals 4, this book, your textbook doesn't tell you about this, but 4 has an s-type and a p-type and a d-type and an f-type. And so n equals 5, you go past F in the alphabet for a G-type and so on. So we're going to talk more about the orbitals. I'm not necessarily going to draw them as such, but you kind of have to understand what an orbital is. It's really a probability plot of where you find the electron, and it is related to the energy.